Okay, so in this video we're going to lay out all of the basic understanding for Gauss's law. And in order to do that, we first have to talk about a Gaussian surface. Now, a Gaussian surface is just a surface which entirely encloses the source of our electric field. So for example, if you had a charged baseball, you could place a beach ball around that baseball, and so that would be something spherical. So here's our charged baseball, and then around that you would have your beach ball. And so our beach ball can be any size we want as long as the beach ball is centered around that point charge and it doesn't come down to the surface of the point charge. So the beach ball could be very large or it could be very small. And so the Gaussian surface just encloses the source that we are considering, those charges that we are considering. Now, there are three fundamental symmetries that we're going to deal with when it comes to Gaussian surfaces. The first one is going to be a plane. And a plane surface is just that. It's a flat plane, okay, like the XY plane or the YZ plane. It's just going to be a flat surface. And we're going to use this as long as we have a uniform electric field and that the surface charge density sigma is constant. The second type of Gaussian surface that we're going to use is cylindrical. And cylindrical is just a cylinder, and we're going to use the cylindrical Gaussian surface whenever we have a line of charge. Okay, and it doesn't strictly speaking have to be a line. It could be another cylinder, but the cylinders, as long as they're centered on each other, they're going to work for Gauss's law. So why do we use the cylinder for a line of charge? Well, if my line of charge is this, then I've got an electric field that points straight up in the YZ plane, or the XZ plane, and then in the Y dimension it's coming straight out of the your computer monitor towards you, and it's going straight in towards you. And so if we take this field or we take this line of charge and we look at it on edge, we rotate it 90 degrees towards us, then we have, there's the line or the wire, and the electric field does this. And the shape which would enclose all that would be a cylinder, where it's going to look like a circle on the end. Think of it as a soup can. Here we're looking at the flat part of the soup can, but our soup can would look more like this if we take this perspective. Alright, so we have one end of the soup can, we'll call that A1, we'll call this A2, and then we have the wrapper of the soup can, but the wrapper is just a plane which has been bent into a circle. And so we'll take a look at all of this in much more detail at a later time. But the important thing to notice is that as you get further away from the line of charge, the field is getting weaker because these field lines, as indicated by these field lines getting further and further apart. So the density of field lines is decreasing. And everywhere a certain distance from that charge, so if we just go out to some radius little r from our line of charge, everywhere along that line the field is going to have the same strength. Now if I go out to a bigger circle like this, then I'm going to have a weaker field, but everywhere along that line it too is going to be of one constant value. And that's what we mean whenever we say that the electric field has to be uniform for whatever symmetry that we're using whenever we're using Gauss's law. Lastly, we're going to look at, or the third fundamental Gaussian surface is going to be a sphere or spherical. And that Gaussian surface, it's going to be used to enclose point charges and other spheres. and that was our beach ball and baseball example up here. Now, keep in mind that these are the fundamental symmetries. We don't have to use these. You could use something like a pyramid if you wanted to. It's going to make everything a lot more difficult, but you can do it, and that's why we're trying to avoid those things. So we want to limit our choice of problems for Gauss's law to those where these are easily applied. Okay, so let's take a closer look at Gauss's law. Formally, Gauss's law is, first of all, the first of Maxwell's equations. You can read your textbook and learn more about James Clerk Maxwell and his contributions to physics. He really, brought together electricity and magnetism. Now, Gauss's law, as formally stated mathematically, is going to be this. The electric flux is equal to Q enclosed over epsilon naught. Q enclosed, this is just the net charge which is enclosed. You see, it's possible that you have positive and negative charges which are inside of your Gaussian surface. So Q enclosed isn't just positive or negative, it is net. It can be a combination of both positive and negative. So for example, if you had a positive charge here and a negative charge here, and we enclose those two charges with a Gaussian surface, with the appropriate Gaussian surface, what we would find is that on this side we've got electric field coming in, on this side we have electric field coming out, and then we've got combinations of going in and coming out on the other parts of our Gaussian surface. And so what ends up happening is, the flux due to this element right here is offset by the flux due to that one. And this one would be offset by this one, and so forth. And so what we find is here, the net flux is going to be equal to 0. And so the net charge which is enclosed is also equal to 0. So Q enclosed just carries with it the idea that the net charge that's enclosed, and that positive and negative charges may be combined. Flux we already know as the integral of E dot dA. So when we write out Gauss's law formally, typically what we're getting is the integral of E dot dA is equal to Q enclosed over epsilon naught. Now, as mentioned earlier, what's happening here is that by knowing the flux, we can infer how much charge is enclosed, and that's what we're doing with Gauss's law. And actually, we tend to use it more for determining what is the electric field for some type of charge distribution, because that's where the real power lies. Let's develop this a little bit more. If you recall from the last video, we said that E is defined by F over Q naught, and that we were going to take this and multiply it by 1, where 1 was just area divided by area. So we ended up with E times A is equal to F times A over Q naught. We said that was really kind of an unorthodox way of writing things, and that we further defined E times A as flux, which also became the integral of E dot dA. Now, F is just Coulomb's law, so that's going to be 1 over 4 pi epsilon naught times the source charge, I'm going to use capital Q for now, times the test charge, little q naught, divided by r squared. and then this is all divided by Q naught, and then we multiply by the area. So some of this cancels out. Q naught goes away, for example. The area can be redefined for a point charge. We're going to use point charges here. The area is the area of the Gaussian surface, and that's going to be a sphere. And so the area is equal to 4 pi r squared. So we get the integral of E dot dA is equal to the source charge over 4 pi epsilon naught r squared times the area, which is 4 pi r squared. So we can cancel out 4 pi, we can cancel out r squared, and what we're left with is the integral of E dot dA is equal to Q, the source charge, over epsilon naught. And the way we typically write the source charge, it's the net source charge referred to as Q enclosed. So this capital Q and Q enclosed represent the same thing. And so you can see we've kind of derived Gauss's law from our understanding of flux. By definition, what it is, it's kind of this natural consequence. Okay, so let's talk about something else here that you may not be familiar with, and that is that little circle that is on our integral symbol. And that just means that we have a surface integral, and we want that surface to be completely closed. So it needs to be a closed surface. And basically that just means that we count the entire surface, that we don't have a hole in our Gaussian surface somewhere. If it's a sphere, then it's a fully enclosed sphere, not a sphere with a hole in it. So Gauss's law kind of looks scary with all this math. You've got this integral with the circle symbol on it. We have a dot product. It's two vectors being multiplied together, and we're setting them equal to Q and then some constant, epsilon naught, permittivity of free space. It looks kind of scary, and yet you keep hearing how Gauss's law is supposed to be really simple and straightforward. And what I'm going to do now is I'm going to show you that this is our formal statement of Gauss's law right here, but when we do Gauss's law, it's going to be actually much easier than that. And so from here down is where I'm going to be demonstrating that for you. So let me rewrite Gauss's law. We have the integral of E dot dA is equal to Q enclosed over epsilon naught. And the first thing we're going to address is this dot product. Now we said, as a reminder here, that we're only going to use Gauss's law in highly symmetric situations. And to be considered highly symmetric, we said that the electric field had to be everywhere perpendicular to the surface or parallel to the normal vector. And so this dot, it's going to go away if everything is parallel. So this goes away because the cosine of 0 is equal to 1. Okay, remember dot product is going to be the cosine of phi, where phi is the angle between the electric field and the normal vector. So rewriting Gauss's law, we get the integral of E times dA, no dot, is equal to Q enclosed over epsilon naught. And then E is going to be constant everywhere, so I can put that outside of the integral sign. So we end up with E times the integral of dA is equal to Q enclosed over epsilon naught. But dA is going to be one of those three fundamental geometries that we're familiar with. And so dA is going to become just A. So we end up with E times A is equal to Q enclosed over epsilon naught. So this is actually the functional form of Gauss's law for virtually all the problems that we do. So the areas that you should consider will be those of a circle. So that's going to be pi r squared. The surface area of a sphere, and that's going to be 4 pi r squared. And then we have the area of the cylinder, and we're only looking at the wrapper part of the cylinder, and that's going to be 2 pi r times the length of the cylinder, which we're just going to call L. So a non-example of using this, remember, this is only the highly symmetric situations. E is always constant. A is going to be some symmetry that we already know the equation for, so we already know what A is going to be. But let's take a look at a non-example. Okay, a non-example of using Gauss's law in this overly simplified version is going to be this. You have a line of charge, and that line of charge is going to create an electric field that points perpendicularly away from it. So that would be here like this, coming out each side, going straight into the board. If we look at it on edge, if we take that wire and we rotate it up so that we're looking, trying to look into the wire as though it were a pipe, we would see the electric field doing this. You're familiar with this by now. All right. And what we're going to do is we're going to enclose it with a cube. And if you enclose it with a cube, all of a sudden our situation becomes this. Put a cube around that wire, and now the electric field, it's only perpendicular at this location, and this location, and this location, and that location. Those are the only places where it's perpendicular. And then everywhere else, the electric field, as it comes through that box, it's coming out at an angle. And so the normal is in this direction. There's our normal vector. And now we have this angle right here, phi, that we've got to consider. So that's the difficulty with trying to use Gauss's law whenever you don't have a constant electric field everywhere along your Gaussian surface, or the angle isn't the same. So the moral of the story is this. You can use Gauss's law for this problem right here if you use a cube to surround a line of charge. But if you're going to do that, then you have to use Gauss's law with calculus. And you really will be doing the integral of E dot dA equals Q enclosed over epsilon naught. If you stick with the highly symmetric situations, then you can use this much easier method where there's no calculus involved at all.